Here's the question that I ended part 1 of this lecture with, and so let's resolve it now. The system is only the particle, and so the only kind of energy the system can have is kinetic energy, and that starts at 0 and ends at 0, so the system's total energy has not changed. And so the work done on the system is 0. That work is 2 different works, one due to the hand and the other due to the electrostatic forces. And so we can say that the work by the hand plus the electrostatic work is 0, and that tells us that the work done by the hand is equal to the negative of the electrostatic work. Notice that we can understand this in terms of the forces. The electric force on the particle is down. The force that the hand must be exerting on the particle to move it up against that electrical force is up. And there is a force displacement vector here pointing up, right? The point of application of both of these forces is at the particle. And so the work that the hand does is in the same direction as the force displacement vector, and so that's a positive work. And the force by the electric field is in the opposite direction, and so it's doing negative work. Here's our negative plane of charge. And let's think about 2 locations, A and B, near it. And we're going to start a charged particle at A and move it to B. And let's think about the work done by the electric force on it. On 2 paths, path 1 and 2, shown in the diagram. I hope you see that calculating the work done along path 1 is going to be easy, because the electric force is parallel to the direction of motion everywhere. What about path 2? Well, we can repeat an argument that I made back in Phys 1104. I can break path 2 up into a series of straight lines to at least approximate it. Now, we know that the work done by a force is 0 if the force is perpendicular to the motion. And so the work done along all these horizontal parts of the path is 0. So what we're left with is the work along the vertical parts. But that vertical distance, if you add up all those vertical paths, is just the same as path 1. And so we get exactly the same work. And so what this is showing is that the work must be the same on both paths. This is exactly the same argument that I made in Phys 1104 for why the work done by gravity is independent of the path taken and only depends on the change of height. In fact, in general, the work done by any non-dissipative force is always independent of path. And so, in fact, this is nothing new. We saw it before in Phys 1104. I made the argument using a particle near a plane of charge because it's easy to picture, because the field due to the plane of charge is uniform. But we don't need a uniform field for the argument to work. Let's think about moving this particle, which is near this other particle. We know that the force acting on this particle due to the other one is always radial, outward from the particle exerting the force. And so we can think of taking this path and dividing it into segments that are radial and segments that follow their own little pieces of circle. Now, the work is 0 along each of these segments that follows its own circle. And so we can simply add up the works along all of the radial segments. Well, now to see how to calculate the work easily, let's define a point here, which I might as well call A prime. And we can see that if we follow a path out to A prime, which is radial out from this charge, and then follow this circle, then it's relatively easy to calculate the work along this radial path from A to A prime, because the force is parallel to the direction of motion, and the work is 0 along the piece of the circle here. And this radial part adds up to the same thing as all these other radial parts that we broke our original path into. And so, once again, this will apply no matter what path we follow from A to B. The work done by the electrical force will always be the same as the work done along this A to A prime segment. Now, suppose this charged particle that we're moving from point A to point B has some amount of charge on it, QP. QP? Why QP? Well, that's standing for probe charge, which should be ringing some bells. What happens if we double the amount of charge on our probe particle? Well, we know that that's going to double the size of the electric forces acting on it. And the work done on it is also proportional to the size of the force doing the work. And so we can see that electrostatic work done on this particle must be proportional to the charge of the particle. And since the work done by the electrostatic forces is just the negative of the change in electric potential energy if we include the source charges in the system, then we can see that electric potential energy must be proportional to the probe charge. Well, this should be sounding awfully familiar. This says that if we know the change in electric potential energy for some unit charge, then we can easily find it for any other charge. And so it makes sense to define a quantity, just like we defined electric field. But now this will be called electric potential, and it's the electric potential energy divided by the amount of charge on the probe charge. Well, just like electric field, this quantity is a property of position and of the source charges. It's not a property of the probe charge. It's independent of the probe charge in exactly the same way that we saw that electric field is independent of the probe charge. I have to stop for a moment and apologize on behalf of physicists who came before me. This new quantity we've met, V, the electric potential, is potential energy per unit charge. But note that it's very closely related to electric potential energy. Well, these are not the same thing, despite the fact that they have almost exactly the same name. Who thought that was a good idea? I don't know. Try not to let the stupid terminology confuse you. As you'll see, this isn't the last piece of really dumb terminology we're going to see over the next little while. So here's an important question. Where is electric potential 0? Well, let's think about this positive plane of charge in two locations, A and B, near it. Each of those locations has some value, VA or VB, of the electric potential. Remember, electric potential is a property of location. And we could start a probe charge off at A and release it, and it'll pass through B later with some speed that we could measure. And so that tells us what the kinetic energy is at the end, and that gives us a measurement of the electric potential energy at the start. However, note that we could have defined the electric potential energy to have been 0 at the start, in which case now, as the particle passes through B, the electric potential energy of the system is negative. The point, as we saw in Phys 1104, is that potential energies are 0 wherever you say they are. It's an arbitrary choice. And so it'll usually make more sense to talk about changes in potential energy. And since electric potential is defined in terms of electric potential energy, it's going to make more sense to usually talk about what we call potential difference, or change in electric potential. Notice, this is all if I'm including the source charges in my system. If I'm not, then I would be talking about electrostatic work done by the electric field. And remember that that's the negative of what I would have got for the change in potential energy if I did include the source charges in the system. And so we can also think of electric potential difference as the negative of the electrostatic work divided by the probe charge.